Everyone, July 29th. Alright, what is it today? Minimum deletions to make string balanced. We are given string S consisting only of characters A and B. We can delete any number of characters in S to make S balanced. S is balanced if there is no pair of indices such that I is smaller than J and Si is equal to B and Sj is equal to A. So what we need to make sure is all the B's on the right hand side, all the A's on the left hand side, and then we want to return the minimum deletion. All right, this one screams DP, right? We have the DP. So basically we can say ending at this, right, to make this satisfy what is the minimum, and we try to see if we can do the next one. And what's an operation? Delete. Delete. To make A on the left hand side and B on the right hand side. So if it's always A, then it's gonna be 0, 0. This is good, it's also 0, and this, right? So looking to the left. Looking to the left. If the left says it's a 0 steps, but now you have a B, that means everything on the left is good. Hold a second. Then you say this A has to be removed. Right, you say this is a 1, and you get another B. This is a 1. You don't have to know, don't have to move. There's an A again. Left is a B, so you have to move again, and then B. I don't know. Is that how it's gonna be? So we just go, and all right. Let's try the second one. I have B, B, A, B, B, right? So if we see the B by itself, it's correct, right? It's always gonna be 0. And this B, if I look to the left is a 0, which means it's already, now like if they're left, so this is in the correct position, so it's a 0. Now this, we look to the left, then you're saying we're gonna have to delete every single one, right? Yeah, that's not right. You don't delete every single one because you can delete these two. Interesting. Okay, so now we have this A, right? So basically we have two choices. One choice is delete myself because I look to the left and the left is a B, so I delete myself. Or you can say if I don't delete my and I delete the things to the left. All right, so we say in this case delete myself is better, so I say in here it's going to be 1, right? In here, or maybe we need to count the number of B's and number of A's. Like so far I have 2 A's and now I have 2 B's, right? And then in order to make it work, I either delete myself, so this is going to be 2, and here if I delete A it's going to be 3, so I deleted 2. Okay, so let's say okay, all 2, and then coming here, right? Coming here, and so far we have 3 B's, right? And then we have, let's say, 5 A's. So we have 5 A's in front of me, and then we have, actually, if we don't count this, we have 2 B's, right? 2 B's in front, 5 A's. So when we come into this, it's a B, right? So I either delete myself. If I delete myself, then it's gonna be 3 steps, right? Because the previous is 2 steps. So either 3 steps, or I don't delete myself, right? I don't delete myself, and I follow previous, so it's gonna be 2 and 2. So what you're saying is we are going to, yeah, let me run the first example. A, B, A, B, B, A, B. We just count. Okay, so we have 1A, 0B, which works because what we want is to, anyway, this is 1A, 0B. This is 2A, 0B, right? 2A, 0B is also good. This is gonna be, so I'm right here, right? I'm at this B. I look to my left, these are all zeros, right? And I look to my left, I know so far is we have 2A and no B. And if there's no, it doesn't matter what, like just what we have at the moment, right? So everyone we can either say, I'll delete myself, right? I can delete myself, so I use the previous, that would be 1. Or I don't delete myself, and I try to fix the previous to make it work. So if I don't delete myself, don't delete myself and fix the previous, then that will be 0. So this one is 0, right? So now I have this A. And this will be 2A, 1B, and so like 2A and 1B. So in this case, actually there are 2 ways to do this. I can delete myself, right? I can delete myself and I use the previous, or that'll be 1. Or I don't delete myself, then I look to the left, then I need to delete all the B's. So that's always going to be 1, right? And then I have 3A and a 1B. And now there's a B, right? I say if I delete myself, that will be a 2 steps. If I don't delete myself, it's going to be the previous when you delete all the B's, which is 1. So 1 is better. Okay, so now there's 3 and 2. So in this case, in this B, if I delete myself, it's going to be 2 steps. All right. If I don't delete myself, I just need to remove all the B's. Not necessarily remove all the B's, right? If I don't delete myself, because this is, it's only if it's A that I need to delete all the B's. If it's a B, you are in the right position, right? This is in the right position, so I can just follow whatever's the previous. So it just be 1. So now it's 3 and 3. Now here is the thing, it's an A, right? Delete myself is going to be 2. If I don't delete myself, then I have to delete all the B's, which will have 3 B's, right? So that's going to be 3. So of course I choose 2. B is in the right position, so I can just continue. Or you can delete it, it's okay, but usually you just continue. Yeah, so basically we say if I encounter a B, doesn't matter what the previous is. If I encounter a B, I just follow. I just follow whatever previous, because otherwise I have to delete it. And then it doesn't really change anything, right? So if it's a B, we just continue. If it's an A, right, then we have 2 choices. Either we delete this A and then continue with whatever we've done before. So it's previous plus 1. Or we don't delete this A and then we delete all the B's in the previous. So we have to have a counter for B, right? So yeah, so what I'm saying is it can be, hold on, I think we have a solution for this one. So we need to keep track of 2 values, right? 2 value. Okay, we need to keep track of 2 values. One is we can call one actually the result. We call minimum delete, right? So minimum delete is 0, and count B, right? And then we say for int, no, we can just char C of S dot to char array, right? If let's say C is equal to B, I think that's an easier case, right? If C is equal to B, then what do we do is nothing changes for the main deletion, right? But count B plus plus. Else, which means it's an A. If it's an A, then there are 2 ways, right? There are 2 ways. we can say min delete shall equal to math.minimum, either min delete plus 1, which is this a get deleted, or count b. We delete all the b's previously. All right, so I think we can do something like that, right? And then at the end we'll return min delete. So let's put the rationale. $16.53. Okay, 16.53. So if just go through string s one by one, right? If the current char is b, right? It is in the correct position, in the correct position. Thus, we don't need to make any further. We don't need to make any change. The minimum deletion, right, will follow the previous value. If the current char is a, there are two options. Either we delete a, or we delete all the b, all the b's before, right? We choose the smaller of the two. Okay, we can actually run a few. So I run these two first, make sure that they work, and then of course these are the, and then something like this, and then something like this, then maybe all A's with a B, all B's with an A. Okay, so we throw a few at it and just kind of see. I think it just goes pretty well, so we submit it, and hopefully it will pass, and it does pass, which means the logic was correct. Fairly fast. I think this one we land on the right solution initially. 3-pass count method, combined pass method, 2-variable method. I think this is the one, right? Count A, minimum deletions, using stack, using DP. Yeah, we immediately go to solution 5. Yeah, this is the one we have. Yeah, we didn't even need to use a DP because you always go into the previous, right? Now you see this one? Right, this is the current. This is before, yeah. Optimize the DP. This is the one. This is the one that we're using immediately. I wasn't even thinking about any of the other solutions. This is the only one that I had in mind. All right, what the hell is a 3-pass? To the left of the character A's and all the characters to the right are B's. Yes, the idea is to find the dividing point that minimizes the number of deletions. For example, the string. If the dividing point is located at index 2, 0, 1, 0, 1, 2. Oh, 2 deletions are required to balance it. I see. So you need a, you need a prefix sum on the count of A and of B, and then go another time. Yep, that's about right. count A plus count B. Yeah, right to left. Count A and count B, minimum deletions. A character to the right, B character to the left. Okay, yeah, makes sense. Combine these. That doesn't make any difference, right? You just kind of do it. Yeah, that's fine. Two variable approach. Do the count. With minus and a plus plus. Okay. Using stack. Removing BA pairs. Interesting. Okay, let's see. Current character A, B, A, so we'll pop. Okay, so we pop. Wait, hold on. Wait, hold on a second. Top of stack B, action, pop B from stack and increment delete count. Okay. And then B, A, pop B from stack, increment. Wait, hold on, let me do this again. A, B. Current character A, top of stack, pop B from character and increment delete count. Oh, this is basically say this is cancelled. Right? A comes in, these are cancelled. So B, A comes in. Wait, it works? Yeah, I think it does work because we are looking for all A's and all B's, right? So anytime a disruption happens, it happens when we have a BA pair. So all we need to do is just to check all the BA pairs. And the easiest way, I mean, if we just want to check BA pairs, why do we need a stack to check the BA pair? We can just go one by one. Find a BA, we just count as one. DP, yeah. I was going for DP. It's pure from analysis, right? It's purely from analysis, but it's basically the same idea because of a BA. Yeah, so like all the B's, which is just following the thing, following the order, which is good, and when it's bad is when A comes in, right? When A comes in. The stack method is quite interesting. But I'm just gonna keep it this way. Close it. I think we have some time today, and then we are try to do this. Find a city with the smallest number of neighbors at a threshold distance. So I think we were not able to do it very well because we did not use Dijkstra. I think this one requires Dijkstra, right? Let me read again. Edges from to weight. Turn the city with the smallest number of cities that are reachable through some path, and the host distance is the most. So yeah, so we're gonna go through every city and I'm gonna run Dijkstra, right? And as we run Dijkstra, we will count how many we get until the weight explodes. And of course, we need to do some Python on this. Seriously, we haven't done Python in a very long time. So let's just count this as a practice. 1, 2, 3, 4. Ooh, hold a second. We didn't do 1, 2, 3, 4 before, right? Yeah, it doesn't matter. 3, 3, 4. Yeah, let's just do this. All right, so what we want is we're gonna Dijkstra this baby. All right, we need a collections import default dicts. All right, that's what we like to use. Graph. All right, that's what we like, and then edges for E in, oh my goodness, hold on. UV weight, right, in edges. Man, it's really hard to do this again because, you know, I'm not really fluent in Python doing this anymore. U and W. Okay. All right. So we got a graph. Then we need Dijkstra. Dijkstra. So what do we need? We need a root, right? And we need graph, which is gonna be a dict of list of tuple. Oh my goodness. We'll call it graph T. Dict list tuple of int and int. All right, we'll call it graph T. What else? Threshold, thresh. Okay, and this is gonna return an integer. So we're gonna say this is gonna return. So we say return the what? Number of cities reachable. The number of cities reachable from root with weights not bigger than threshold. Okay. So now what we're gonna do, then Dijkstra is weights. You probably need, oh my goodness, I probably need n as well. I mean, I can use counter. All right, technically you can use counter, but all right, let's just use n. We have n. Let's just use n. Okay, so we can just say 0 times n, right? That's the weights. Then we need a q. Oh, okay. Now we need to say import priority heap q. There we go. All right. So we need to say q equal to this. Okay. And then actually no, we need to put root and 0, right? Okay, now while q node and ACCW, right? Q dot, is that pop? Yeah, I think it's pop. Wait, hold a second, that's not right. Sorry, I think it should be heap q dot heap pop q. Okay, so we got a node, we got ACCW, and that's the accumulated. Okay, so when do we do the count? So we need to count how many. Okay, I like to count. So okay, count is 0, right? Then we say for child weight in graph node, right? So I have a child and a weight in graph node. If accumulate weight plus w is smaller or equal to threshold. Two things. Okay, two things. If accumulated w is not equal to weights node. All right, continue. And here we have two things. If this is smaller than weights child, okay. Oh my goodness, this has to be math.inf. There we go. Then weights root shall equal to 0. Okay. Graph node. It's unknown, right? Wait, hold a second. Graph. Argument of type int cannot be assigned to parameter key. Oopsie doozy, I forgot. This is gonna be int. There you go. If it's smaller than that, okay, then we say weight child shall equal to ACCW plus W, right? Q dot heap Q dot heap push child and ACCW plus W. All right, so new weight ACCW plus W and ACCW, okay, hold on, W plus W, okay, VFW, C, new W, next change, okay. So I'm gonna push this in and count plus equal 1, all right? Done, coming back, and then at the end we'll return count. Okay, all right, so this is a count. Find the city. All right, find the city. If there are multiple cities, return the city with the greatest number. Oh, so we also need to sort at the end. Return the city with the smallest city that are reachable through some path. Whose distance is the most. If there are most cities, return the city with the greatest number. The distance, sum of the edges. Okay, so now we can say min weight, okay, math.inf, rest is equal to -1 for I in range n, okay. Is it 0 indexed? Yes, 0 indexed. We can say current weight is equal to self.extra I graph distance threshold, and if current W is smaller than smaller equal to main W equal to current W, and then rest equal to I, and we'll return rest at the end. Okay, let's try. Expected one more position. Ooh, heap push, that's correct. We forgot a Q. Tuple is not defined. Dear me. Tuple. Oh, shoot. All right. Let's see if this one works. Oh, that was bad. The first one is not right. Okay, did I do the Dijkstra wrong? Oh yeah, I did the Dijkstra wrong because you didn't even use the threshold. My bad. If it's smaller than this and new weight is smaller or equal to the threshold. Okay, so we just need to copy this line. Yeah, that's an oversight. Oopsie doozy. Okay, try it again. Interesting. I get to 0. How? Oh, it's easy to do. We just need to, holy crap, it's a lot of things. Let's get a new one. Temporarily I'll save it here and just focus on this one for now. What I want to do is trying to see what's the current weight. So we can say print I and current weight. Oh, it's not current weight. It's not weight. This is not returning a weight. This is returning a count. Yeah, this should be returning a count. It's not weight, it's count, min count. My bad. It should be min count. This is just count. Alright, so if count is smaller or equal to, my bad, min count. Right, if smaller or equal to min count, then min count. It doesn't affect the count. Now this is count. Okay, 0 count is 2. That's correct. 1 is 4. Oof, 1 is wrong. The threshold is 4, so 1 have 1. 2, 3. Oh, I see, because this one gets counted twice. Because it reaches the first time. I see. Okay, no count. So reachable. Should be easy to solve. There you go. That's all we need just to all we need to do is to avoid the double count. There you go. Yeah, so Dijkstra works. Should work. There we go. Was faster actually. Right, this is Java, this is Python. Yeah, Dijkstra definitely works. It is Dijkstra. We need to do something. Wait, what's the Dijkstra runtime? O-N n square OM log n. OM log n is Dijkstra. OM log n is Dijkstra. Okay, so Dijkstra is because a heap Q we put in the node log n, right? And we have to go through all the edges. So we can just say Dijkstra is OM log n, where m is the number of edges and n is the number of nodes. Since m is equal to n minus 1 divided by 2, I think that's the requirement, right? Edges length, yeah. Dijkstra is on squared log n. Right, on the outside, we loop through all the nodes. Thus, the total runtime is on tripled log n. Yep, it makes perfect sense. Make perfect sense. Oh my goodness, Bellman-Ford. So there's always Bellman-Ford, Floyd-Warshall, and they seem to be able to replace Dijkstra. What does this do? A graph search algorithm that finds the shortest path from a single source to all other vertices in a weighted. So Floyd-Warshall is finding the smallest, find the minimal weight for all pairs. Okay, all pairs. Bellman-Ford is finding the smallest path from a single source to all other vertices in weighted graph. Can handle graphs with negative edge weights, making it more precise but potentially slower. Do we have negative edge weights? I don't think we have negative edge weights. No, we don't. Wait, Dijkstra cannot do negative edge weights? Really? Dijkstra cannot do negative edge weights. Why? Why Dijkstra cannot do negative edge weights? Because of the... I don't know why they cannot do negative. Distance to all vertices infinity except the source, which is set to 0. This in addition represents our initial state of knowledge. That's not for you, Jimbo. You just take Jamba's position. Alright, we start by initializing distance to all this at infinity, except the source vertex, which is set to 0. This initialization represents our initial state. We don't know any path yet, so we assume they are infinitely long, except for the trivial path from the vertex to itself. Next, we perform the key operation relaxation for each edge in the graph. We check if the distance to the destination vertex can be improved by going through the source of that edge. We repeat this relaxation step v-1 times, where v is the number of vertices. This worst case, where vertices form a line, it might take v-1 step for change to propagate. We apply Bellman-Ford from each city as source, giving us the shortest path from every city to every other city. We could have used a single source and run Bellman-Ford once, then repeat it for other sources, but running independently for each source simplify our code. Yes. We can't, Don't have it. Simplify. Simplicity makes a good algorithm even if it's not the most efficient. Okay, I need to see the code. Just by looking through this, I don't really understand. And in my TLE. Alright, so how do you do Bellman-Ford? Let's see. Oh my god. Okay, let's go Python. It's easier to understand. So Bellman-Ford. Where is Bellman-Ford? Is this Bellman-Ford? Okay, the city with the shortest distance. No, I don't think this is Bellman-Ford. This is Bellman-Ford. Distance from the source is going to be infinity. Distance from the source, okay. Shortest path is in source, set as 0. Relax edges up to n-1 times. So we go through n-1 times. Start and... Oh, we don't even have to set up the graph. We'll just go through all the edges. So it's very similar to Floyd-Warshall, right? And we say if shortest path start is not this, and shortest path start plus weight is smaller shortest path to end. So we just say from start going to the end, right? From the start, we have a start and end, right? If from start the path start plus the weight is smaller than, then we update it, right? We say the end should be this, update equal to true. If and is not equal to, so it's a reverse, right? It's a reverse, we do it. If not updated, break. Stop early if no updates, which means we have handled all. Interesting. Now this is very simple. I agree, this is very simple. Break out if no updates are made. If no updates are made, that means what? I think it says the update. Yeah, so basically this is just saying we go through all the edges, and if an edge can make things better, right? If it can make things better, then we do it, right? And we have to do it both times. Yeah, so this is very, very similar to Floyd-Warshall. Floyd-Warshall is pairs, right? We have two pairs, any pair, and we have a third node. We're saying if including the third node can make it better, right? If it can, then we just say yeah, we can. If not, we have Floyd-Warshall here, I think. Is this something I want to try? Yeah, Floyd-Warshall's here. And if you look at this, Floyd-Warshall is doing this, right? With the mean cost. So we get a mean cost. Hold on. Floyd-Warshall, we can have the mean cost. And can be improved, right? It can be improved. And the initial mean cost. So these two are very similar. Okay, Bellman-Ford is very similar to Floyd-Warshall, and both can be, I would say, a simplified version in terms of the structure of the code. It can be simplified compared to Dijkstra, but Dijkstra is king. Okay, Dijkstra is king. And both can be solved within Dijkstra. Well, it would just be interesting. Interesting. I don't think. Do we want to implement Bellman-Ford? Man, the whole purpose is to close this window. If we want to do Bellman-Ford, then we have to try it again tomorrow. Yeah, we should do Bellman-Ford tomorrow. Yeah, we should. Oh, look at this. What the hell is this? I've never seen this before. It's similar to Bellman-Ford, but instead of blindly relaxing all the edges, it uses a queue to keep track of which verses need to be processed. I begin by adding sorts to the queue, then enter a loop that continues as long as the queue is not empty. Each iteration will remove a vertex and relax its outgoing edge. If relaxing the edge updates the distance, we add a neighbor. This is you're reinventing. This is you're almost reinventing Dijkstra, right? You're reinventing Dijkstra at this point, right? You're reinventing Dijkstra. Why you do this? Floyd-Warshall. Yeah, I guess it works, because it's all pairs, right? It's all pairs. And if it's all pairs, then you can always find. I think if you do Floyd-Warshall, you do it once, right? I think you do it once. Let's see, do you have Floyd-Warshall? This is Floyd-Warshall, you do it once. You do Floyd once. You don't have to do it multiple times. Yes, you do it once and then you, yeah, you do it only once. You know what? I'll do that. Yep, Floyd-Warshall. I'll do that. I think Floyd-Warshall is better than Bellman-Ford. If you want to do Bellman-Ford, you might as well just go with Dijkstra. But Floyd-Warshall is a simpler, much simpler algorithm. It does run in ON triple. I'm not sure if ON triples. Yeah, it will work. It will work. Good. All right, we're not doing Bellman-Ford. We will do Floyd-Warshall next time. All right, that'll be it. That'll be it for today. Oh, hello. Didn't see you there. Now you do this. So first of all, I'm not good at this. Okay, I do a lot, but I'm still not like really good at this. I still struggle. But I mean, these things you keep doing it. You keep doing it. You'll see problems more often, and you get used to it. You see the problem. You're like, I think this probably is a graph, right? This probably is a DP, and you kind of just know how it's solved. But still, hey, I'm definitely not the best. There are people way better than I am. Yep, that'll be it. I'll see you guys tomorrow.